And now I have the pleasure to welcome Professor Elison Matioli, Associate Professor. He's heading the Power Lab laboratory that develops semiconductor for technology in the field of power and RF electronics and also thermal management. He joined EPFL in 2015 after a postdoctoral fellowship at MIT. The floor is yours.
Thank you very much. Good afternoon. Today I'd like to talk about emerging technologies for the future of electronics. So electricity is becoming one of our basic needs in this century. And it's quite clear when you see the extent that people go just to get a little bit of charge these days. So in this talk, I would like to talk about the specific charger there, or more generally, the power converter. And before I talk about this, I would like to motivate my interest by looking at the evolution of computers. So back in the days, computers used to take up an entire room. And then we had the demonstration of a first laptop, 1990. And today we have these amazing computers that we can carry in our pockets. All of this was basically possible because of integrated transistors. So we have today more than 1 billion of them in a single chip. Now let's look at power converters. Let's look at the charger for this first laptop. So in 1990, this is a 45-watt charger. And this is a 45-watt charger that we have in 2024. They look about the same. They're still based on single discrete transistors. So the vision that we have is, could we integrate power transistors in a single chip and have integrated power chips in the future? So that would open amazing opportunities, just as like we had for computers. For that, we need to look into materials that can withstand very large voltages in a very small footprint with very little resistance. So in my lab, we're looking into gallium nitride, aluminum nitride, even diamond for that application. Let me give you an example of how we can make high-efficient devices. So if we look at a typical gallium nitride transistor, electrons need to be conducted through a single channel. And there is a trade-off between the carrier density and the mobility. So if you try to put a lot of electrons in a single channel, there's a point where they are no longer mobile. So you actually are limited in the conductivity that it can have. So in our lab, we propose to use multiple channels. So basically, we can have a lot more electrons, they're a lot more mobile, and with that, we can achieve ultra-low resistance and very high efficiency. Just as an example, a multi-channel device here with 5 channels, we can have 5 times less resistance than a single channel. With diodes, we can have 5 times more current than a single channel device, all of them with the same footprint. So then we demonstrated devices that can withstand 1.3 kilovolts and have resistances that are much smaller than the typical resistance that you find in common devices today. So this can offer a pathway for more efficient power electronics. But then the question is, if we want to go to integrated power circuits, the second challenge is on thermal management. So if we look today, the power converters, they're based on single transistors, all on a PCB, and then you attach these big pieces of metal, for example here, to extract the heat and throw to the environment. Of course, if we go to an integrated power chip, question is, how can we extract the heat out of that? So in our lab, we decided to integrate tiny tubes inside the chip itself, very close to where the component heats up. So if we look here, we flip the power chip. Inside it, we have a network of microtubes. We can flow liquids inside the chip now. It absorbs the heat, and it's extracted. So by doing this, we now can have multiple power transistors and connected together with these microtubes. If we look from the top, it looks just like a normal device, but inside we can see channels that can extract the heat very close to where the device heats up the most. So with that, we could achieve performance that are orders of magnitude better than a typical fan and heat sink. and also extract much higher power out of the chip, up to 2 kilowatts per centimeter square. So we demonstrated a full power converter. It's actually using liquid cooling. We got 4 times higher power. It's a tiny little thing. It looks like a coin. It converts half a kilowatt, and the peak temperature is still below that of air cooling with 1/4 of the power. So that shows this is one of the highest power density converters that has ever been demonstrated, 78 kilowatts per liter. Once we demonstrated this, we got a lot of questions whether we could use this kind of technology for the cooling of CPUs in data centers. So if you see here a CPU, to extract the heat, we attach this big piece of metal with a fan, so we blow the hot air to the environment. Not only that, when you look inside the CPU, the heat is not generated in a homogeneous way. So we have spots of high heat flux, spots of low heat flux. So we then started a startup called Corinthus with the goal of to solve the question of how can we apply microfluidic cooling to optimally cool down this kind of heat map. So the idea here is we first developed a software that can generate the best microfluidic pattern for that particular heat map. So here you can see the software calculating in real time. So after some time, the software gives us the best geometry to cool down optimally that kind of heat pattern. Then we go to the typical fabrication tools. We can make entire silicon wafers with this map. And then we can make heat sinks that are a fraction of the size of the ones that I just showed and can optimally cool down the inhomogeneous heat map that we have in CPUs. So with that, I hope to have shown just 2 examples, both in electronics and in thermal, that we believe to help to have an efficient electrification of our society in the future. So thank you very much.